Good day everyone, this is Optical Mark Recognition System. To begin, let's look at the high-level RTL or Register Transfer Level architecture of our Optical Mark Recognition System. At its core, our OMR row grader is a digital signal processing module. The architecture is divided into two main stages, a combinational logic stage and a synchronous sequential stage. In the first stage, row 8 will sensor data representing the physical darkness of bubbles. A, B, C, and D enters the system alongside the dynamic threshold value. Parallel combinational comparators evaluate this input instantly. In second stage, driven by the system clock, the logic determines the total number of marks. It categorizes the row as a valid answer, a blank, or an overvote, compares valid answers against the system answer key, and logs the final error codes and grading status into the output registers. Moving into the specific code implementation, our design relies on a few critical functional blocks. First is the thresholding function. To maintain clean, modular code, we created a reusable function called checkshade. This function takes the 8-bit density value of a single bubble and strictly compares it against our threshold. If the bubble is darker than the threshold, it outputs a digital 1, otherwise, it outputs a 0. We run this function 4 times in parallel for bubbles A through D. Second is the summation block. We concatenate and add the digital outputs of the 4 bubbles. This gives us a 3-bit total marks vector telling us exactly how many bubbles on that specific row were shaded. Third is the validation and auto-grading logic. This operates inside the clock process. We use a priority evaluation tree. First, if total marks is exactly 0, the system flags a 0, 1, blank, error. Second, if total marks is greater than 1, it flags a 1, 0, overvote, error. Third, if total marks is exactly 1, the system successfully decodes which specific letter was shaded. It then immediately compares the student answer to the provided answer key. If they match, the is correct signal is driven high. Comparing VHDL and Verilog, implementing this in both languages revealed their distinct strength. In VHDL, the code was highly structured and strongly typed. We had explicitly defined data types like unsigned and carefully managed type conversions to add our signals together. While verbose, the strictness prevented data mismatch errors. Conversely, Verilog provided a much faster, C-like development experience. We utilized Verilog's ternary operator and straightforward wire/rec assignments to achieve the exact same hardware result with much cleaner, more concise code. To verify the correctness of the RTL design, we developed a comprehensive mixed language test fixture. The test bench operates by instantiating our OMR grader as the device under test. We generate a simulated 10 nanosecond clock to drive the synchronous logic. For our stimulus, rather than writing out every case manually, we engineered a scalable testing loop. Using a for loop and a case statement, the test bench automatically cycles through 10 distinct testing scenarios. These scenarios don't just test perfect inputs, they stress test the system's edge cases. We inject data representing perfectly shaded bubbles, completely blank rows, double-shaded overvotes, and even smudged papers where multiple bubbles have background noise, but only one crosses that threshold. By viewing the output waveform, we verify that our system successfully handles both academic grading and robust error classification with a single clock cycle latency. In conclusion, the design and verification of the Optical Mark Recognition OMR row grader successfully demonstrated the practical application of digital signal processing by accurately evaluating sensor thresholds, detecting overvotes, and auto-grading responses. Implementing the system in both Verilog and VHDL highlighted the comparative strength of each language. Verilog's concise syntax for rapid development versus VHDL's strict data typing for structural integrity. Ultimately, the use of scalable, mixed language test benches to validate critical edge cases reinforced essential functional verification and debugging skills, proving the design's robustness and serving as a strong foundation for industry-standard FPGA and ASIC workflows.